Okay, welcome to Mathematical Induction. We have a thrilling discussion today about how to prove something by mathematical induction. So, let's say we are asked to prove or disprove that 3/5 plus 6/5 plus 9/5 all the way up to, let's see, what should I put there? What should the nth term be?
N plus 3?
N plus 3.
No. That's not. I take that back.
That was retracted. Notice what you're doing secretly here is you're building a sequence.
Yeah. I know you're adding 3 every time.
Okay, we're adding 3 every time. What kind of a sequence adds 3 every time? An arithmetic sequence. Good to sort of refresh these things. And so, what do you do to add 3 repetitively?
3 times n minus 1.
Okay, so you might have something like 3 times n minus 1. Well, if the first term's 3 and the second's 6 and the third's 9, that doesn't quite work out. What would I have there?
3n.
Just 3n. And I'm debating with myself. There's some piece of me that would like you to sort of show this, but I think I want to do an inequality. Let's see whether or not that is less than, say, 3n squared over 5 for all natural numbers. Okay. Now, just because of space, you better have that written down because we're going to have to sort of reuse it. Okay. So the first thing is I have to sort of decide, use sort of an educated guess to decide whether I'm going to try for proving or disproving. So theories. You might want to go over here and do a little scratch work.
I would just think since you're squaring the second one that was automatically always, because the n is automatically always going to be larger on this side than on that side. But
Well, so, you know, I'm just sort of checking that first term. If n was 1, you'd have 3/5. I guess those are equal. So it's at least believable there, but I guess it's not always greater than. We could try the second one. 3/5 plus 6/9 6/5, sorry, is 9/5, and 3 times 2 squared over 5, let's see, that's 4, so that's 12/5. So that seems true. You know, well, is the 4,000th one true? I don't know. That's why we need mathematical induction, right? So, if we were going to, so I guess judging from these two cases, I'm going to try and prove it, not disprove it. By the way, what would constitute a disproof? A counterexample, exactly. So, all I need to disprove this statement is to give you one number. I could say, not true. For n equals 82, show that this inequality doesn't hold. Okay? To prove, we go as follows. I say proof by mathematical induction. Okay, what do I start with?
Step 1 base case.
Step 1, which is the base case. And what is that base case?
1.
N equals 1.
N equals 1. So, to begin with, and we've done that over sort of in our scratch work, if n equals 1, the left side is 3/5. And then I want to say, is that less than or equal to, so this is sort of the thing that's in doubt. Is that less than or equal to 3 times 1 squared over 5, which is, let's see, this is 9 on top?
No, it's 1 squared, which is 1 times 3 is 3 on top.
Good, good. So 1 squared, remember order of operations is paramount here. 1 squared, do the exponents first, times the 3. So this is indeed true. And we are set. Okay. Now, I'm going to cheat a little bit here. This is the line that I'm going to use in step 2. But because I have limited board space, here's what I'm going to do. Don't you wish you could do this? Step 2. How does your step 2 start?
Assume for all.
Assume that the statement is true.
And that there's a number k that can replace
Or n equals k. Okay. Well, what's that mean? That means that our old statement is true, taking out an n and writing in a k. So that's the nice thing about reusing my board, right? So that's what you write, but you might be thinking in your head, if the statement is true for 7, is that same statement true for 8? So you might sort of think, I didn't even write a k. I told you to write a k, but I didn't do it. How's that for hypocrisy? Okay, so if you were thinking about a 7 here, and this statement, you know that it's true for 7, could you prove that it was true for 8? And likewise, if it was true for 8, would you know that it was true for 9, and so on. So here's what we'd like to do. I'd like to have a big, long proof, and I'd like to end up with this statement at the bottom. Thus, this thing is true with a k plus 1 in both those places. So thus, 3/5 plus 6/5 plus 9/5 plus 3. I want a k plus 1 in here. I need to put parentheses because the whole thing needs to be multiplied by 3/5 is less than or equal to 3 times k plus 1 squared over 5. And the statement holds by induction. That's going to be the end of my proof. How do I take this, that's the thing I'm allowed to assume, and reach this? Well, I'm going to say thus, and I'm going to start with the left-hand side of what I have, and I'm going to work my way somehow to the right-hand side. Sound good? So the thing about mathematical induction is a large part of the proof is just sort of knowing the structure. We haven't gotten to the part that really requires the algebra yet, or really requires the insight. But if you can't sort of get to here, you're not going to even get a chance to play the game. So we're going to start with this. Thus, 3/5 plus 6/5 plus 9/5. Now notice that this goes through, this piece here, goes through 3k over 5 before it gets to 3k plus 1 over 5. So this is really rewriting the left-hand side here. I'm just writing in explicitly this term. What am I going to do now? What's that actually equal to? This is what I'd like to have. What do I know?
Why is it 8
Well, it doesn't have to be. Would you like one of these?
I was just,
Do I know something it's related to?
if you add this simple thing to the other side, 3k squared over 5.
Ah, okay. So I know that this red chunk is less than or equal to that. So I can take that chunk, and indeed, you're right. If I'm going to replace it with something that I know is at least as large, I have to put that same sign, and I'll replace this with 3k squared over 5 plus 3k plus 1 over 5. The way you should think about this is you know that's true, and so this has been added to both sides. Okay, well, then the left-hand side looks fine. The problem is I want this right-hand side to look like this. What do I do?
Can you put them over the same since they have the same common denominator?
Okay. If they didn't have the same, we'd get a common denominator. Because they do, I'll write an equal sign. Now, if you compose a less than or equal to with an equal to, okay, notice what you get out is a less than or equal to. If I know this is less than or equal to this, and this equals that, I know this is less than or equal to that. Right? So 2 is less than 3, and 3 equals, I don't know, 15 divided by 5. That means 2 is less than 15 divided by 5.
I have to run.
Okay. Then we have what here? Well, we have 3k squared plus 3k plus 1 all over 5.
We factor 3 out.
We factor out a 3. Squared. This is what I have.
You have 3 k's right now, so I don't know how you would.
Well, what is this? I mean, so I have k plus 1 squared. Maybe I should just sort of think about this off to the side. Let me sort of think about, here's my thought bubble. What is k plus 1 squared?
K plus 1 times k plus 1.
K plus 1 times k plus 1. And what's that equal to?
K squared plus 2k plus 1.
So what's the problem here?
Can't be factored into.
Well, I have my k squared. I have my 1.
You don't have enough.
You don't have another k. Well, if I'm just trying to maintain inequality, and you'd like a k, though, certainly this thing is less than or equal to the same thing with an extra k, right?
Well, yeah. But
So-
what principle allows you to add another k?
Yes. So maybe I should just write in 2k plus 1 there. So certainly this is less than or equal to that. Now, if you're kind of uncomfortable about just sticking it in the middle, then this is what you could do. You could go clear back up to, say, this step, and you could say it's less than or equal to this plus 3k. Then you could just factor that out, and you would get now 2k there. Notice if you worked here, you would get 3k and 3k, which is 2k's times 3. So however you want to do it, the most the most standard version is the way we did it to start with, which is just to say, well, certainly k isn't any bigger than 2k. So here we are, and what does that mean? Well, I'll erase my little thought bubble.
How are you allowed to just stick another K in the problem?
Well, I'm allowed to, as long as I'm good at putting that symbol. If you're trying to say that something is less than something else, you can always stick in something on the bigger side or take off something on the smaller side. So this is what I have. I can stick in something if I just want it to be bigger, right? So if you happen to know that 2 is less than 3, and you want to compare it to 10, well, there's no problem saying that this is less than 10, and then using transitivity there. Here, you could actually think about if it's equal to, it's certainly less than or equal to. You have 4 less than or equal to's. So you combine them. And you get this. And then I would go straight to the end of my proof here. Why? Because I think you could see from this that this equation is equal to this. I'm just rewriting that term. So that is my proof. And I might put a little box at the end, or QED, or some such madness. Some people put lightning bolts.